Hello there. Dark stuff and the fate of the universe. It's a nice way to bring this topic to a conclusion. We're going to look at dark energy, dark matter, and how that may affect the fate of the universe. It's just a little sentence really on the end of the specification that wants you to understand that there's a lot more that we don't know about and we're trying to find out about. For example, dark energy and dark matter. Exactly what they're going to ask you about that we think will be very limited, but it can do you no harm to learn a bit more about it. Dark energy and dark matter, do your best not to mix them up. So here we go. I'll try and get you to understand the theory now. We'll start with dark matter. Fritz Zwicky came up with this. This is an awesome name. So we are here in the Milky Way galaxy, right? In a spare and an arm, and in the Milky Way galaxy, and we're orbiting the centre of the Milky Way, 270 kilometers per second. So we're going around here at 270 kilometers every second, and yet it takes us 225 million years to get around. So it's a pretty big circumference that we've got to make our way around. You get the idea. Now, what affects that? So imagine that you are moving around. This moving around here is going around in a circle, and that's circular motion. Now there's a reason why these hammer throwers in the Olympics are very rarely, very often just full of muscle, because they have a lot of power. They need to pull incredibly hard. So it would be very hard to throw it a long way without huge amounts of muscles to be able to accelerate that little hammer greatly. So what does that mean? That means that you can't just swing it around fast without the strength and the force to pull it. Okay, so it's not just technique. It's not just a lasso thrower's technique. We need the force. So essentially what happens with circular motion is, and we look at this in more detail when we look at satellites, is you pull it towards you. You get it swinging, and then when you've got this horizontal motion coming here, you pull it towards you. That deflects it a little bit. When it's up here, you pull it in. So this person here is constantly pulling it in, changing its direction. If you let go, we're just straight that way. If the ball was here, you let go straight that way. So you don't let go when the ball's facing where you want it to go. You let go when it's to the side and it's actually traveling in that way. So circular motion may be something to try and get your head around. You could swing something on the end of a string, do it safely please, and when you let go, just observe which way it moves. And if you want it to go forwards, you might let go in the wrong place until you work it out. So the point I'm trying to make from this, is that the force applied makes it spin faster. The bigger the force, the faster it spins, which is why they're full of muscle to get a great big force so it spins fast. Obviously, the faster it's spinning, the further it will go in the Olympics. Okay, the bigger the force you apply, the faster it will spin. That's circular motion. It's important for satellites as well. There's a Lego thrower, Lego hammer thrower for your enjoyment. All right. So here we are in the Milky Way, another different type of diagram here, artist's impression, and we are shooting along. And if gravity, the centre of the Milky Way would be around here. If gravity suddenly switched off, then we'd just go straight that way. We'd carry on in the way we're going. But gravity constantly pulling us in, turning us around. Yes, there's gravity pulling us that way, but there's more gravity pulling us that way. So the resultant gravitational pull is towards the centre of the Milky Way. So we rotate around it. Okay, so the bigger the force you apply, the faster you will spin. Applies not only to hammer throwers, but also to anything circling around the centre of a galaxy, or to anything going around the Earth, or for anything going around the Sun. Okay, the force is gravity. That's the only force happening in space there. So gravity is the force that is pulling you towards the centre of the Milky Way. So the bigger the force, the faster you spin. So we understand that now. So here's Isaac Newton. And Isaac Newton, not when he was hit on the head with an apple, but when he observed a comet, figured out that gravitational force of attraction between two objects depends on two things. One would be the product of their masses. So the mass if you want to know the gravitational force acting on the Earth, you need to know the mass of the Earth and the mass of the Sun. And the second thing is how far away they are. Obviously, as you go further from the Earth, gravity becomes weaker. As you go further from the Sun, the gravitational pull of the Sun will become weaker. mass and distance. So gravity depends on mass of both objects and the distance, or their separation. So, here's the thing. If we add up all the matter we can detect in our galaxy, then we figure out we know the mass of our galaxy. So that would tell us how much gravity there is in our galaxy. Then take that information over to the laws of circular motion, and we can calculate how fast our galaxy should spin. And we could work out how fast every galaxy should spin by estimating the mass of each galaxy, just by trying to count the stars, I suppose. And here is the bombshell. This is how fast the galaxy spins, the y-axis, and x-axis is the distance from the center of our galaxy. So, as you go further, ignore the middle bits, but as we go further from our center of our galaxy, you would expect the speed of the spinning to drop off. So as we go further from the center of our galaxy, you would expect the speed to slow down because you're further away, so you feel a smaller force, so you don't spin as fast. And we have observed B. So there seems to be no great drop-off as you go further from the center of the galaxy. What does that mean? Well, either our understanding of gravity is completely wrong, or our measurement of distance is completely wrong, which you don't think it is, or third option, our measurement of mass is completely wrong. And that is what we thought to be true. Our measurement of the mass of our galaxy we think is wrong. We think it's way too small. We think there's a huge amount of mass in our galaxy and in every other galaxy that we couldn't detect and we couldn't see. So it was invisible to us. So that mass or matter got referred to as dark matter, matter that we couldn't see. But we can detect it because luckily gravity, huge gravitational forces will bend light. So you get something called gravitational lensing, which I won't really fully explain this image here. So there he is, there's Fritz. And Fritz came up with this idea because of the speed that the galaxies were rotating. Dark matter doesn't interact with the electromagnetic spectrum. So it's not giving off any light rays, any radio waves, any infrared, any ultraviolet, and that's how we detect things in our universe. We use the electromagnetic spectrum. So if it doesn't interact with the electromagnetic spectrum, we're in a bit of trouble trying to detect it. So we can't detect it directly, but we can detect its effects. So we can detect its gravitational effects, which are huge. Okay, so that is, I would say, that's the key to understanding what dark matter is. Dark matter was kind of put as the reason why galaxies were spinning faster than we thought they should. So it led us to believe that there was more matter around than we thought there was. But we just couldn't detect it. Dark matter. It's pretty well accepted now. Dark matter, this matter that doesn't interact with the electromagnetic spectrum. And believe it or not, there appears to be a lot more dark matter than normal matter. And that's dark matter dealt with. Next, we're going to move on to dark energy. So will the universe keep expanding is a question. Now, you can imagine the universe, it's a nice little model for the expansion of the universe when you draw dots on a balloon and blow up the balloon, because it shows you that every dot moves further away from every other dot at the same time. That's the only way you can get that to do that. If you stretch the balloon, you wouldn't get the same effect. So everything moves away from everything else because the whole thing is expanding. So, here's the universe. And the only force that really acts in the universe that we are aware of is gravity. And gravity brings the universe back towards itself. So the big question for many years was, will the universe keep expanding or will it contract into itself? And the only question we really had to answer was, is there enough gravity to bring it back into itself? The universe expands, so gravity, the gravitational effects is getting weaker as it goes, but it's still there. So will it in time pull it in back towards itself? So you could essentially have something after a big bang, and then it could expand out and then come back in on itself in form, cause a big crunch, as they referred to it. Or maybe it was expanding so fast that gravity would never win over, it would never bring it back, and it would escape and just be what they might refer to as a big yawn, just expand out forever. You could think of a model for that on the Earth. So actually, there's something called an escape velocity. So if you fire a cannon up into the sky, it's going to come back down, isn't it? If you fire it faster, it'll come back down a bit later. There is a speed above which you could fire that cannonball and never see it again. So that had escaped. Gravity would lose out because it had gone so fast. So if the Big Bang was fast enough, it will never collapse into itself. But if it wasn't fast enough, it will collapse into itself. That's what we were trying to figure out. So we were trying to calculate the speed of the expansion of the universe. We assumed it must be slowing because gravity's pulling it back. There's only one force, so that must be decelerating the universe. We observed it, and in trying to calculate how fast the universe was expanding and how much it was slowing down, they made a shocking discovery. And that shocking discovery was that the expansion of the universe was speeding up. Speeding up. Hang on a minute. There's only a yellow force here. That's the only force. You can't accelerate that way when the only force is inwards. So what was going on? Gravity's the only force that we knew about. So we led to either these theories, a big yawn or a big crunch. Okay, ignore that. But then we came up with this idea. Because it was accelerating, we thought, well, the resultant force must be outwards. So dark energy got the blame for that. So that was the phrase coined to mean the force or the energy that is causing the universe's expansion to accelerate. And, it wasn't too hard. We used Type 1a supernovae, if you're interested, which are standard candles, and that means they are of known luminosity, so we could find them. But also they show a history. The further away they are, the longer ago they happened. So we kind of get a history of the expansion of the universe by observing these exploding stars. And yeah, so it's expanding, which was a shocking discovery. So now there's more at play than just gravity. So there's some other force that seems to be pulling out. Or, I suppose, another option, it could be pushing out, couldn't it? It could be this all matter repelling all other matter, this kind of anti-gravity idea that's stronger than the gravity. We really don't know at this stage. So the point of this being on the specification, it is lovely. It's nice that they've put this on to make you realize that we are way off knowing everything, and we never claim to know everything. And there's certainly in astronomy and in everything else, there's huge areas of research that are going on, and there's millions of questions that we're desperate to know the answer to. Sometimes you have a problem, and you try and find the answer to that problem by doing loads of research. Sometimes you just have a question, and then maybe you figure out what the uses of the knowledge that you find are later down the track. But yeah, we are very interested in this, and there are people right now working on theories about dark energy. Alright, so this is a nice little diagram, I suppose. You can think of dark energy as expanding the universe, but don't forget it's got a bigger job on its hands now because there's more gravity because of dark matter pulling it in. So dark matter's pulling it in, and dark energy's pulling it out or pushing it out, and dark energy seems to be the winner at the moment because the universe is expanding at an accelerating rate. This is a common diagram that you see, and this is about the rate of the expansion of the universe here. So at first, you can think of the size of the universe as kind of the diameter of this, and you can notice that it's starting to curve up. So we think that in recent times, that curve up, you can think of it as like a distance time graph. So any curve up would be an acceleration. But yeah, if you go back here, in this period of inflation, which is certainly not on the course, that was an unbelievable expansion rate. which again we don't really think followed the laws of physics, which is a confusion. So desperate to explain that, and desperate to explain why the size of the universe seems to be expanding at an accelerating rate. So here's some shocking figures for you. We think about 23.3% of the universe is made up of dark matter, and 72.1% is made up of dark energy. So that leaves about 5% is made of atoms. Right? So there's an example of how we see gravitational lensing affect things. You see, if we look at a distant galaxy, then that light won't travel in a straight line, it will curve. So you could essentially see the same thing twice. If you look that way, you'll see the light coming in from there, but if you look that way, you'll see the light coming in from there. It's an extreme example, but yeah, you can see the same thing twice because it bends around something massive. Okay, so that's how we first detected dark matter. Here's a nice little graph. Here's a moodier graph. I like this graph. It's changed, some of the percentages ever so slightly, and it's not a perfect, we don't know this for certain, but it really hammers home the point that I'm afraid you've been studying physics with me for a long time. We've really only been studying 4% of the universe. I've been hiding the other 96% from you, trying not to mention it really in case, you ask lots of questions about it. But yeah, it said, what's the point? It says there's only 4% of the universe. Shouldn't we be studying the other 96%? And I'd have just brushed it off and said something light-hearted. But yeah, that seems to be the truth. In reality, that 4% is the universe around us that affects us. So that's why we're interested in it. But yeah, a pretty dramatic graph there to finish up on this section. Okay, so that's dark energy and dark matter. To summarize, it's only a tiny little mention in the specification, which deals with you understanding that there are certain unknowns, and there's huge areas in astronomy that we're desperately trying to find the answers to, and two of the biggest examples are dark matter and dark energy. I would not expect an essay on dark energy or dark matter, but to be able to answer a 2 or 3 mark question on what it is. So just link dark matter to why galaxies spin too faster than they should, and it doesn't interact with the electromagnetic spectrum, and dark energy is linked to the acceleration of the universe's expansion. I will leave it there. I hope that was helpful. Thank you very much.